All right, so today we're going to talk about the mean value theorem. So we said a little bit about it in our limits chapter, but what the mean value theorem states is that it says if you have a continuous function on a closed interval, so the interval must be continuous on the endpoints and differentiable on the open interval. So that means that the endpoints do not have to be differentiable. So that's very important. So when we have like the absolute value of x here, if we went from 0 to 1 on that function, the mean value theorem would apply because it is differentiable on the open because it's not differentiable at 0, and it's continuous from 0 to 1. But if I said from -1 to 1, that would not apply. Sorry, it looks like it's getting all yucky on there. It would not apply from -1 to 1 because it's not differentiable at the 0. So make sure you understand the difference. So it's differentiable on the, or it's continuous on the closed, so it has to be continuous, defined at both endpoints, but it only has to be differentiable inside of the interval. So it does not have to be differentiable on the endpoints. So what it says that if this is true, then there exists a number where the derivative, so that's right here, f prime, so the derivative is going to equal the slope between the two endpoints. So whatever your slope is between the two endpoints, it's going to equal it. So I'm going to draw you a little picture up here and see what we're talking about. So if I pick like a point here and here, there's the slope between those points. At some point in the interval, it looks like probably right about here, then that is going to equal the slope. So you see how they're parallel now? So that's what the mean value theorem says. The slope between 2 points equals the slope at 1 point. So if we're going to use it down here, so we're going to go from 0 to 2. So when we do this, we're going to practice a lot before we review for the exam because they want to make sure that you guys are very good now at stating the condition. So you'd have to state that it's continuous on the 0 to 2, and then it's differentiable from 0 to 2 also. So including it or not including the endpoints. So what we do is we plug in 0. So we need to get points because what we have to do right here is to find the slope. So I'm going to plug in 0. I get out 0. I'm going to plug in 2 into the function. So we're doing 2 squared. I see that we're having a lag on the picture. Sorry. So 2 squared is 4. And we have to find the slope. So y minus y over x minus x. So 4 over 2 equals 2. So the slope between 2 points has to equal the slope at 1 point. So remember, this means derivative. So the derivative of that is 2x. So we're going to set these equal and figure out where that occurs at. So you do 2x equals 2, so x equals 1. So the c, so typically you can use c if you want, it depends. So the c is 1. It's an x value though, so I typically use x, but the AP exam won't differentiate between the two as long as you have that the value is 1. So this right here, I usually, when I'm in class, try to trick you guys because you never remember what the square root of 1 minus x squared is. That is a semicircle because remember it's a 1 minus an x squared with a radius of 1. So it's going to look like this, like if it was on the endpoint. Sorry, it's a bad picture. So we should be able to know that the slope here is 0, but let's just go ahead and check it. So it says find a tangent of the function, the interval, that is parallel to the secant. So that's another way to say use the mean value theorem. Right, so this wording is the same as mean value theorem. So this right here is saying find your y values. When I plug in -1, I get out 0. When I plug in 1, I get out 0. So 0 minus 0 over 1 minus -1, 0 over 2 equals 0. So that's 0. That's what I had said the slope was going to equal. And it should equal it at 0 up here, but let's go ahead and prove it mathematically. So now we have to do the derivative. So the derivative of this is 1/2. Remember, this is a chain rule. So multiply these together. So I get a -x over square root of 1 minus x squared. That's going to equal 0 when the top equals 0. So remember, fraction equals 0 when the top equals 0. It's undefined when the bottom equals 0. So this is just -x equals 0. So x equals 0. All right, so by definition here, a function is increasing on an interval. It says that if x1 is less than x2 implies y1 is less than y2. So that should make sense. So as if I'm going up a hill right here, this x value is lower than this x value here, and then this y value is lower than that y value. And then obviously the opposite is true for decreasing. The corollary, which is what we like to use a lot in calculus, it says that if your derivative is positive, that function was increasing. And if your derivative is negative, then that function was decreasing. So this is what we use to determine increasing or decreasing, because most of the functions we don't know what they look like, so we have to talk about what the velocity, which is slope, is doing. So something simple like x squared, we know that x squared looks like this. Let me move my picture up some for you. So we know that it's decreasing from negative infinity to the vertex here at 0, and then it'll be increasing from 0 to infinity. But let's prove it algebraically. So the derivative is 2x. So it says that we have to first figure out where it equals 0, and then we're going to test it. And this is kind of what we're doing in 4.1. So set this equal to 0, so x equals 0. So we're just going to put it on a number line and test it. So if I plug in negative 1, remember you plug it into the derivative. Plug it into the derivative. If you plug it into the original, that is a y value. I want to know what slope is. You want slope. Increasing and decreasing are slopes. So plug in a negative 1, you get negative. Plug in a positive 1, you get a positive. So that tells me that this is decreasing. So it is decreasing from negative infinity to 0. And it is increasing from 0 to infinity. That also would tell me, minus the positive, would tell me that I have a minimum at 0, 0. And no, I plug the 0 back in there to get my y value. And this would be an absolute min because there's no one lower than it, but that's what we talked about in 4.1. It's a minimum. Some corollaries that should make sense to you. All right, and so this won't be in your Delta Math today, but it is something that they throw in your book in this chapter, so I want to throw it in here too. So the idea here is that we have an antiderivative, and that's really what calculus is about going backwards. So we've spent the entire first part of this year going forwards, and once we get to chapter 5, we're going to spend the next 3 chapters going backwards. So this kind of just throws it in there in this section of just thinking about what the original function would have been. So if my derivative is 3x squared, I want you to pause for a second and tell me, and think to yourself, what would the original function have been? And then once you know, or you can't think any longer, then unpause me and get the answer. So the original function would have been an x cubed, because I brought down my power, subtract 1. So again, same thing. Pause your video and then come back here to get the answer. So for b, so this is the same thing as 1/3 x. So it tells me that my exponent was a square on it. And then I had to have brought it down, so that gives me a 1/6. So watch, if I bring down the power, that gives me 2/6x, and that's the same as 1/3 up there. So you got to think backwards. Again, pause for C, and then get your answer. All right, answer. So if the function's cosine, that means it was sine. Now, the other thing behind all of these is that this could have been x cubed plus 3, x cubed plus 7, x cubed plus 10. So we put plus c behind all of them to say that it could differ by a constant. Honey, go in there. So let's just practice some more increasing and decreasing functions. So extrema means max or min, and then this is increasing or decreasing. So for all of these, you have to take a derivative. So 5 minus 2x. Sorry, hold on a second. Hang on. David, go in there. She's talking to you. All right, sorry. So take the derivative and equal this to 0. So that gives me x equals 5/2. We're going to test it. Remember, we tested in this function here. So plug in 0, I get a positive. If I plug in like 4, I get a negative. So this tells me that it is increasing from negative infinity to 5/2. It is decreasing from 5/2 to infinity. And that makes this a maximum. So your maximum is 5/2. Plug that into the original and get out your y value, which I'm not like doing right now. All right. So, and then, big word. If they say value, I think we talked about this. Value means the y value. We want the y. So if they ever ask you what's the maximum value, make sure you get the y. All right. So this one, derivative. So this is the same as that. So negative. So set this equal to 0. So it's equal to 0 nowhere, but it's undefined at 0. So we're going to test 0 to see if anything's happening, but it's not defined here. Even the original is not defined, so it cannot be a max or a min. But it could tell us what the function's doing. So let's plug in like -1. -1 comes out positive, and turn out 1. And then 1 is still a positive. Oh, wait, these are both negatives. Sorry. Because I forgot there was a negative right there. Okay. So it tells me my function is decreasing the entire time, but it's not defined at 0. So we would say it's decreasing on its domain, and its domain's negative infinity to 0 and 0 to infinity. So did you notice I use parentheses? And that's because it's the domain. Over here we use brackets because it's actually defined at those points. It's not defined at 0. So it'd be increasing nowhere, and there's no extremas on this one. All right, so the last one here, product rule. Leave the first alone times the derivative of the second. And don't forget this is a chain rule because you got to do times the derivative of the inside plus second alone derivative of the first. So I'm going to pull out this to see if it helps me. So I'm going to pull out a 4 minus x to a negative 1/2. And that gives me a negative half x. And if I take that out here, that's going to leave me with a 4 minus x. That gives me negative 3/2 x plus 4. So this is going to be undefined at 4. So let's check 4, all right, because that's on the bottom. So we check undefined and we check zeros. Set this equal to 0. Flip and multiply. So when we get x is 8/3. So then you would check. So 8/3 and 4. All right, so let's plug in 0 into the derivative here. So that would be a positive and a positive. And that's what, 2.6. So if I put in like 2.7, 2.7, that's still positive. 2.7. Let's see, plug in 5. Sorry, you get to hear my thinking. So 5's not defined. So it's not defined after 5. Do you see that up here? So this is going to be a negative here. I might have done that wrong in my head real quick. But let's see. I believe that's correct. Let me see real quick. So you get to see me do mental math without a calculator right now. Yes, that's a negative. I was right. All right. So that'd be a negative here and then a positive. And so it's not defined after 4 in the original function. So we'd say it's increasing from negative infinity to 8/3. It is decreasing from 8/3 to 4. So this right here would be considered a max. So we have a max at 8/3, whatever the y value is. You just saw how long it took me to do the other mental math. And if I plug in 4, then let's see, that function's going up and then down. So this would be a minimum. So then I have a minimum at 4, 0. That's easy to do. All right, so just a few more to do the mean value theorem. So mean value theorem here, remember you plug in your 0. So you get 0, get negative 1, plug in 1. So 2. So 2 minus negative 1 over 0 minus 1. Oh, wait, I did that backwards. So 3. So then I do the derivative. So 2x plus 2. And I'm going to equal it to the mean value theorem. So subtract that over. So 2x equals 1. So x equals 1/2. So the value happens at 1/2. Let's see. Plug in 1 sine. Sine inverse of 1. Let's see. So what value does sine? So that's my y value. So where's my y value? And this is just going to be probably the first quadrant answer. So my y value is 1 at pi over 2. And at negative 1 would be at 3 pi over 2. So then I do 3 pi over 2 minus pi over 2. Negative 1 minus 1. So that gives me a pi over negative 2. All right, and then the derivative of that, I believe, is 1 over the square root of 1 minus x squared. And then we'd equal that to pi over negative 2. And then you'd solve that right there. So your assignment today should be mostly satisfying your mean value theorem, I think. And I think I have some, and then there's one section on the extrema. So derivatives equal to 0 and then test them. Should be those right there. Email me if you guys have any questions.